Hello everyone, my name is Ignat, thanks for tuning in, and today we're going to talk about how to speed up disk encryption in Linux. First, a little bit about myself. I work at Cloudflare, I mostly do performance and security. I'm passionate about security and crypto, and I also enjoy low-level programming like Linux kernel, bootloaders, and other low-level carry C stuff. Okay, so let's go. Disk encryption. Before we dive into Linux disk encryption specifically, let's first discuss about how to encrypt data at rest in general. And there are many ways to do that. And to review all of them, we probably want first to review the typical operating system storage stack and all the different layers it has and how disk encryption can fit in between. So at the top of any storage stacks, you have your application and services which run on your hardware. And so these applications typically read and write data in files. So they send these files to an operating system primitive, a file system, and then the file system typically translates these files into some kind of blocks because most modern uh, persistent storage are some kind of block devices, so they read and store data in blocks. So file system translates files into blocks. But file system cannot communicate with storage hardware directly. There is usually another layer in a modern operating system, which is called block subsystem, which knows how to talk to specific storage hardware. So file systems send blocks to the block subsystem, and then block subsystem sends these data blocks to particular storage hardware. So with respect to disk encryption and encrypting data in trust, we can probably insert encryption at each of these layers. So first of all, we can just encrypt. We can just buy hardware which supports data encryption, and there are some couple of standards around that, which is SAD, SED, which stands for self-encrypting drives, and OPAL standard. Secondly, we can just encrypt the data as it passes through the operating system block subsystem, and here we have the examples of LUKS dm-crypt on Linux, which we're going to talk about in this presentation. We also have the BitLocker for Windows and FileVault on macOS. We can encrypt data in the file system layer, and here again we have some examples of implementations in Linux, like eCryptFS, which is an older one, or a newer one. It started as a ext4 encryption implementation, and later it became more generic, and it's now called fscrypt. And finally, of course, we can encrypt or decrypt data directly in our applications. So there are many applications which support encryption decryption natively. They may use some kind of encryption libraries like OpenSSL, Themis, or PGP. Let's review pros and cons of each approach. So first of all, you can, as I mentioned, you can just buy self-encrypted drives, and they're quite easy. The pros of these solutions is just there, and you require very little configuration to encrypt your data. It's also this approach is fully transparent to the application, so the applications do not even know or care if the data stored is being encrypted, because that's handled for them by the lower layers, especially the storage hardware. And it's usually faster than any other layers because the encryption is implemented in the hardware itself, and you don't waste your main operating system CPU cycles to do the encryption. The downside of the approach is that usually you have no visibility into the implementation. Most of these self-encrypting drives have proprietary firmware, so you have no auditability, and which sometimes leads to poor security. And one of the recent security findings around the self-encrypting drives were so bad that Microsoft eventually decided to use software data encryption by default in their Windows operating system. Then we move upper up the stack, we have our block layer encryption. It's very similar to storage hardware encryption, but it's implemented actually in software in your operating system. And it shares some of the characteristics. So again, you need little configuration to configure it. Again, it's fully transparent to the application. The upside of this, if you have an open source operating system like Linux, it's also open and auditable. You can look into the implementation and make sure it's as secure as you would like it to be. There are downsides, of course. It requires somewhat specialized crypto, because we already know that modern storage devices are block devices, so we need to encrypt or decrypt data in blocks, and that is not something which most crypto algorithms can do, because they are based around file or stream encryption. So there are specific cipher modes which are designed specifically for storage disk encryption, but they don't receive as much attention as the typical crypto we're all used to. There can also be some performance issues, because now you have to use your main CPU to encrypt and decrypt data, so there might be some we obviously waste resource, so there might be some performance degradation here. And there also, like, unlike the hardware disk encryption, the encryption keys are now stored in RAM, in the main operating system memory. So if, for example, our operating system becomes compromised, an attacker can actually grab that disk encryption key. Then there is file system layer encryption. It's like block layer encryption. It's somewhat transparent to applications. It's also open and auditable if you have an open source operating system. Unlike block layer disk encryption, it's more fine-grained, so you can have like encrypted and unencrypted directories in your file system, and you can have different directories with different encryption keys. There is also more choice of crypto and potential integrity support, because the file system layer has the visibility of a file, so it can use either cipher mode, but only the block cipher modes for block storage. There are downsides, of course. Again, there are performance issues, because we use our main CPU to do the encryption and decryption. As other software solutions, we have our encryption keys and RAM. It's more complex configuration, because all these fine-grained abilities, we need to provide like fine-grained configuration to actually make it work. And the one downside is that people notice is the unencrypted metadata, because usually with file system encryption, the data in files are encrypted, but not the metadata around these files, like file names or file sizes, as well as free space on the disk is not encrypted as well, which provides some side channel attacker. And of course, you have the application layer encryption. It's open and auditable, well, mostly because if you as an application layer developer have to implement it yourself. It's very fine-grained, so if you're a developer, you can implement whatever you want, and you have full crypto flexibility. You can encrypt if you like. The downside, as other software implementations, so you have your encryption keys and RAM. You have to actually code it, where all the previous approaches were somewhat transparent, so the applications do not need to have support in their code for data encryption. Now we have to actually write that code in our application. Also, we have the unencrypted metadata, so we can only encrypt the data we're going to write in files, not the rest. And one of the downsides, I think, is again full crypto flexibility. Not every developer has the experience or proper knowledge to implement cryptography right, and sometimes that may lead to very poor security, and the overall solution becomes not secure, even though we use some encryption in the application. Okay, so let's move to Linux. Why Linux? Cloudflare, like most SaaS companies, prefer to use block layer disk encryption because from the service perspective, from SaaS perspective, you don't usually need the fine-grained abilities that application or file system layer provides, but you also want more security. But on the other hand, we also don't want to rely on insecure hardware and, well, basically introduce potentially bad and unverified crypto implementations in our stack. So that's why we choose open source Linux disk encryption. But before we dive into dm-crypt, which is the disk encryption implementation on Linux, we need to review device mapper first, because dm-crypt is a device mapper module. So what is device mapper in Linux? Again, we have our applications, and we already established that they do read and write files from the file systems. Then the file systems translate these files into blocks and send these blocks to block device drivers. So device mapper framework in Linux can insert itself in between the file systems and the block device drivers and provide some additional functionality. For example, we have the dm-raid module, which can help you to build software RAID arrays on Linux. And particularly for this presentation, we're interested in the dm-crypt module, which provides transparent disk encryption to the data before it gets to the block device drivers. So let's zoom into the dm-crypt module. Again, we have our file systems and we have the block device drivers. So what dm-crypt does, it inserts itself as the rest of device mapper modules in between the file system and the block device driver. So when a file system needs to write a block to the block device driver, dm-crypt intercepts it and encrypts it and sends it down the stack. When the file system needs to read some data from the disk, it reads the data, decrypts it, and then sends the decrypted result to the file system. And on top of that, dm-crypt doesn't implement its own crypto, which is good. It uses the Linux kernel standard crypto API, which is open source and have been around for a while, so we hope it received very much attention from the security community, and it's probably secure enough for most of the use cases. So it was all well and good, but at some point we noticed that our service is not performing as we like it to be. So the performance was poor, and we started to trace it down, and we realized that part of the performance degradation was attributed to the transparent disk encryption. So we decided to benchmark it more thoroughly to understand what it means. Basically, for this specific benchmark, we want to avoid any potential bias a typical storage hardware might have, so we decided to remove storage hardware out of the picture. This would help us share the results with other developers outside of the company, and they can probably reproduce the same results because they may not have access to a specific storage hardware. So instead of using a real disk for this benchmark, we used a so-called RAM-based disk, which basically a virtual disk emulated in RAM. And on Linux, you can create one very easily with the PRD module. So this command, for example, creates us a 4 GB RAM disk. Now, to test disk encryption, we need to allocate a 2 MB separate file. It's called lux detach header, and I will explain why we need a detach header in a second. Then we just prepare our new virtual disk for encryption. We format it with lux, and then we instantiate a dm-crypt instance on top of our RAM disk, so we get an encrypted RAM disk. So here's our test storage stack. So at the bottom layer we have our virtual RAM disk. On top we created a dm-crypt instance which provides transparent encryption and decryption of data. And as a file system, we will not use any file system for this benchmarking, just because, again, we don't want to introduce the bias of a particular file system implementation into the result. Instead, what we can do is we can read and write data to this dm-crypt instance directly, which will be transparently encrypted or decrypted by the operating system. And we can compare that throughput by reading and writing data to the underlying virtual disk directly, bypassing the encryption layer. And that's why we actually needed the 2 megabyte LUKS header. We needed a detached header, because if we use the default non-detached header, that header would be stored on the underlying virtual RAM disk, and if we do the unencrypted read and write operation into first 2 megabytes of the disk, we may accidentally erase that header and break the whole setup. So this LUKS detached header enables us to read and write data both to unencrypted disk and encrypted disk without the risk of breaking the setup. Okay, let's first check what is the throughput of our RAM disk, basically the throughput of our RAM before we do any encryption. And we can create artificial I/O workload. We have like 4K block I/O, and we do some sequential read and writes. And if you run this, basically we can see our virtual RAM disk has throughput somewhere around more than 1 gigabyte per second for both reads and writes. And the numbers are similar because it's a RAM disk, and RAM, it doesn't like reads and writes usually have the same speed. Now we redo the same test, we rerun the same I/O workflow, but now using the dm-crypt encrypted instance on top of our RAM disk. So all the data we're going to read and write will be transparently encrypted or decrypted. And here we see that the throughput suddenly drops to 100 and somewhere around 150 megabyte per second. And yes, we do understand that now we're encrypting the data, we're wasting some CPU, we're spending some resource to do that, but basically it's actually more than 7 times slower, which is probably not we were expecting to see. But what is the normal data? So to calculate our desired data of what we can get, we decided to follow this approach. So the crypt setup utility has an embedded benchmark, which we can use to benchmark the performance or the throughput for a specific crypto algorithm. So we use ISXTS as a default in dm-crypt and LUKS, and this tool shows us that the raw performance of the crypto itself, raw throughput, is somewhere around 100.8 gigabyte per second. So if we assume the worst case, let's say if we just read the whole data from the disk and decrypt it later sequentially, the combined throughput of the whole system should be still somewhere around 700 megabyte per second, but we are actually getting only 300 megabyte per second of combined throughput, which is more than half than the expected worst case. So we tried to optimize our setup. We tried switching to different cryptographic algorithms, but ISXTS seems to be the fastest, at least on x86 platforms. We tried experimenting with dm-crypt optional flags. So dm-crypt has some specific so-called performance flag, the encrypt CPU and submit from crypt CPUs, which the man page indicates that they may improve performance. We tried those, they didn't help. We also tried to move from disk layer encryption to file system layer encryption, because we would probably encrypt less data. We don't encrypt empty space, file system metadata, and so on. But in the end, it was still much slower and potentially less secure. So We were in despair. We tried everything and nothing helped. We were so desperate, so we decided to write about our findings in the dm-crypt mailing list. But all the answer we got is this. The answer we got is, if the numbers disturb you, then this is from lack of understanding on your side. You are probably unaware that encryption is a heavyweight operation. And at this point I was wondering, is really crypto can be that expensive? So I decided to do a proper scientific research on that topic. And by proper scientific research, what I mean is I typed, is crypto expensive, into Google search form. But surprisingly, one of the top results I got is a blog post from our own company, the Cloudflare blog post, where one of my colleagues investigate the performance of crypto, but not in the context of data encryption and rest, but in the context of TLS. So Cloudflare terminates a lot of TLS connections, and so yeah, we do a lot of TLS handshakes, and also we encrypt a lot of data we send over the network. And the colleague of mine investigated what are the costs associated with that. And surprisingly, the conclusion is that using TLS is very cheap even at our scale. And modern crypto is very fast, with ISGCM and P256 being great examples. So in this post show that like Cloudflare uses less than 3% CPU basically for TLS encryption. So if encryption is so cheap for TLS, why should it be very expensive for disk encryption? Because under the hood they mostly use the same crypto algorithm. So this is where we decided to take a closer look into the disk encryption implementation in Linux, and we find some interesting things. So again, we have our file system, we have the underlying block device drivers, we have the dm-crypt, and we have the crypto API to actually do the encryption. Turns out, when the file system issues a write request, so the file system wants to write a block, the underlying block device, dm-crypt intercepts it, but it doesn't process it immediately. It doesn't encrypt it and send it to the block device driver. Instead, it has a queue implemented in dm-crypt itself called kcryptd, and it queues that request for some time. Then, when the time is right, dm-crypt sends that request to the crypto API to actually being encrypted. But modern crypto API is asynchronous as well, so it may not immediately encrypt the data. It may also queue it internally. And unlike dm-crypt, which has one queue per dm-crypt instance, crypto API has one queue per CPU. So the more CPUs you have, more you have. But still, the request may spend some time in this queue. Then when the time is right, the crypto API encrypts the request and sends it back to dm-crypt, but dm-crypt does not dispatch it immediately. Instead, it stores it into another queue, which is basically a red-black tree for sorting. Then it sorts these requests, but does not dispatch it immediately. Again, it stores it on yet another queue called dm-crypt write, which later, when the time is right, actually sends the data to the block device drive. Similar things happens on read. When the file system wants to read a block, dm-crypt doesn't read the data immediately. It stores the request on yet another queue called kcryptd. Then, when the time is right, it actually sends the request down the stack, reads the data. When it gets the data back, it doesn't decrypt it immediately. Again, it stores into our familiar kcryptd queue, and sometime later dispatches it to the crypto API, where the crypto API can queue it again. It can basically then, when the crypto API decrypts the data, it sends it back to the file system. And that's a lot of queuing to just process one single block read or write. Last year I was at SRECon in Singapore, and there was a nice presentation from Google engineers about the relationship between the queuing and the tail latency in computer systems. And this is a great presentation on its own, and I encourage everyone to watch it. But one takeaway I got from there is a significant amount of tail latency is due to queuing effect. And basically this is what we see here. And in this particular implementation, a single request can be queued up to 4 times before actually getting to be processed. We assume no malicious intention, so like if these queues are in there, so there must be a reason. Luckily, most Linux source code is in source control, is in Git, so you can actually do some browse the history and see why these specific queues been added. So I decided to do some Git archaeology, and some of the finding that the kcrypt DQ was there from the beginning when the initial dm-crypt implementation was merged into the Linux mainline, but it was only for reads. With the comment, it would be very unwise to do decryption in an interrupt context. Some more queuing was added to reduce so-called kernel stack usage in 2006. Then offloading writes and IO sorting, that red-black tree, was introduced somewhere in around 2015 with the comment that this will improve performance for spinning disks, but may improve some SSDs. It also mentioned that it's better for CFQ scheduler, but actually this scheduler is being deprecated now. And we're not on the first ones who saw the performance degradation for this excessive queuing. So there, like immediately in 2015, we can see some commits which actually add these flags which we already tried before, same crypt CPU and submit from crypt CPUs, which actually disable some of these queues. But all that tends to believe that this is what was some time ago, and the landscape changed a bit. So based on all this archaeology, what we understand is that most code and most that queuing was added with spinning disk in mind, where we have disk IO latency was much higher than the current scheduling latency. So it was very easy to add this asynchronous behavior because the context switching of a CPU thread was negligible compared to the spinning disk IO latency. Sorting a block IO request in dm-crypt probably violates do one thing and do it well principle, a Unix principle. So dm-crypt is for encrypting and decrypting data. Performancing should probably not live in dm-crypt, and it's probably the task for the IO scheduler instead. kcrypt was basically added because back in 2005 the Linux crypto API was synchronous, and that's why, as the comment mentions, we need to avoid an encryption operation in interrupt context. The kcrypt was added, but modern crypto API is asynchronous as well, so kcrypt may be just redundant. So we decided to try to clean it up. We decided to throw away all this extensive queuing and logic and basically convert this implementation back and make it fully synchronous and make it look like somewhere like this, like we thought it would like to be. So basically dm-crypt just encrypts and decrypts data without any additional logic. And on top of that, we wanted to avoid even the asynchronous behavior in Linux crypto API, so we wanted to make Linux crypto API synchronous as well and see how far can we go. So we did a simple patch for the dm-crypt module, which bypasses all queues or asynchronous threads based on a new runtime flag. With Linux crypto API, it's a bit more complicated. By default, Linux may have different implementations of the same crypto algorithm, and the specific implementation is selected by the kernel based on the configured priorities. But we all want to avoid that kernel making decision, and we wanted to force our implementation to use ISNI, which is x86 hardware accelerated crypto on our servers. But sometimes an ISNI implementation needs FPU, floating point unit, but in Linux kernel, sometimes you cannot use that floating point unit in interrupt context. So we came up with this new crypto API model called xtsproxy, which is a dedicated synchronous XTS model. But we know that it's very dangerous to roll your own crypto, so this module does not implement any crypto on its own. Instead, it's just a simple switch, where if in the current context FPU is available and it happens like 99% of the cases, it just forwards the encryption or decryption request to the already present in the Linux kernel ISNI implementation. And in rare cases where we cannot use FPU and thus ISNI, we direct it to the more generic software IS implementation, which doesn't require the use of FPU. But still, it's all synchronous. It doesn't have any asynchronous behavior or threads. It processes data as it comes in. So let's benchmark our setup. So we restart our synthetic I/O workflow on our encrypted disk. Luckily, because we implemented this as a runtime flag, we can already start our I/O workload and reconfigure the way how the kernel encrypts data later, just underneath the application live. First of all, we just need to load our new custom xtsproxy crypto API implementation into the kernel, and then we run this very scary command to enable our patches. And this command basically does two things. First, it tells dm-crypt not to rely on the kernel to select a particular IS implementation for us, but explicitly tell it to select our new xtsproxy module for IS encryption. And secondly, we basically enable our the flag introduced by our patch, which tells the dm-crypt itself to bypass any queuing or asynchronous threads into the implementation. And finally, for the settings to take effect, basically we need to do this suspend and resume operation. And basically this is the result. This is the read throughput from our encrypted ramdisk graphed on a fancy Grafana dashboard. You can see, and this here we can clearly see the point where we enable our patch in runtime. So before we had less than 150 megabyte per second of read throughput. After enabling the patch, we almost more than doubled our throughput, above 300 megabyte per second. And we see the same picture with writes as well. When we enable our patch, the write throughput jumps more than 100%. And thus, now we have both 300 megabyte per second of read throughput and 300 megabyte per second of write throughput. Totally, we have 600 megabyte per second of total throughput, which is very close to the worst case upper number of 700 megabyte per second throughput we calculated earlier. So we eliminated most of the performance bottleneck in crypto implementation. Just to make sure we're not imagining things, this is how the effect of our patches on our real production system. So this is now not a virtual RAM disk. This is a real SSD from our production system. And the yellow line shows the perceived latency, I/O latency of the raw SSD itself. And the green line shows the perceived application latency from the dm-crypt instance on top of the same disk. As you may notice, when we enable the patch, these latencies converge. So from application's perspective, now there's almost no difference in terms of latency. It uses an encrypted disk or not. And this is Cloudflare service impact. So this is the three-way comparison of Cloudflare cache T99 response time measured over 5 minutes on 3 servers. So here we have a server with just plain SSDs, unencrypted SSDs. This is a green line. Then the red line is the same service run on the same server with same hardware configuration, but the disks were encrypted with standard Linux disk encryption, and you can see we have these very high spikes of T99 response time from our CDN cache. And then the blue line shows the same server but with our patch enabled. And here we can see that the encrypted server is now almost indistinguishable from the unencrypted server. So from the Cloudflare service perspective, we basically get the disk encryption for free. We see no difference between encrypted servers and unencrypted servers in terms of service latency. That's basically it. That's what I wanted to share for today. So in conclusions, in this presentation we introduced a simple patch which may improve dm-crypt performance by 200 and sometimes 300%. It's fully compatible with stock Linux dm-crypt. It doesn't introduce any new crypto. You don't have to re-encrypt the drives, even your encrypted disk, to use this patch. You can just use it as is. And basically it can be enabled and disabled in runtime without any service disruption, even if your server is serving live production traffic. We reassured ourselves that modern crypto is fast and cheap, and when you have a performance degradation, don't rush to blame crypto or security. A performance degradation may be likely elsewhere, like for architecture. We see that extra queuing may be hard on modern low latency storage, so the whole concept of data encryption and rest should be reassessed with respect to modern low latency storage like SSD or NVMe SSD. There are some caveats though. This patch improved performance on small block size, high IOPS workloads. Like we tested it on a 4 kilobyte block size. Starting with block sizes of more than 2 megabytes, these IO workflows do not show better performance and even some degradation, so there is room for research there. That the current setup assumes that we have hardware accelerated crypto in the CPU, which most modern x86 systems use, but the result is that our current xtsproxy modules heavily relies on x86, so it supports only x86 platform. And basically your mileage may vary. Don't rush to enable this unconditionally in your setup. Try to measure, try to benchmark it, try to compare side by side, like your specific IO workload with or without this patch, and see if you get an improvement. If you get some meaningful results, even good or bad ones, please let us know. We would like to get more data to see how it can be improved in the future. Finally, here are some links. First is the link to the source code of the crypt setup utility, which is the user space helper tool to encrypt disks on Linux. Second is the man page for DM setup, low-level utility from Linux, which to manage device mapper devices and this dm-crypt devices in particular. The third link is the link to the blog post, which contains all the information I described today and even more measurements, so I encourage you to go and read it. The fourth link is a link to our Cloudflare Linux repository, where we published the patches I presented and talked about today, so you can basically go grab them and try them out yourself. And finally, luckily, since the first time I presented this presentation, this work was basically accepted in somewhat reworked form. It was accepted into the mainline Linux kernel, so you may be able to experiment with this approach with Linux kernel starting from 5.9, which is currently in release candidate still, but it will be available in mainstream Linux pretty much. That's all. Thank you for the attention, and I'm now happy to take any questions you might